Michal Kocvara, and we all fight against linear semi-definite optimization. He's the one guy who really can handle nonlinear semi-definite optimization with his code Pennon. So there's not too many around that really try to do nonlinear semi-definite optimization, and he has, in my experience, always wonderful applications and the perfect code for it as well. So please, Michal.
Thank you. Can you hear me? I guess you can. Yep. Okay, so first I should answer the question, why the hell do I want to speak about nonlinear semi-definite optimization when the linear one is complicated enough? And you know, when you hear about semi-definite optimization, people don't usually say that it's linear because they assume that it's automatically it's linear, but it doesn't have to be. So we may have a nonlinear function of matrices which should belong to a semi-definite cone, and then we get nonlinear programming. Okay, so just to fix the notation, so what I want to solve is a problem like that. Let's say we have a variable x, standard variable. We minimize a matrix. We minimize a function f subject to inequality constraints. And so far, that would be just standard NLP. And I just want to add one more constraint, saying that a matrix should be positive, semi-definite, and that matrix in SDP it would be just a standard linear operator, but in my case it can be a nonlinear operator from Rn to the space of symmetric matrices. Right. Okay. I don't really need to go through that. That's very standard. So let me skip that. Also here, so I just wanted to recall the linear SDP, the primal and the dual pair. So some people call that dual, some people call that primal, the first one, and here we have the corresponding second one, the dual problem. Okay, so we all know that linear semi-definite programming, and we have seen it in the last 2 days, many applications from let's say mathematical applications like in eigenvalue optimization or in robust programming, up to true industrial applications like in chemical engineering, structural optimization, in machine learning, and there are many others. It's just exploded in the 90s, in fact. So the question is, why do we need nonlinear semi-definite programming or nonlinear semi-definite optimization? Are there any applications of that at all? And okay, so I'm trying in the last years, I'm trying to collect these applications, and I will present some of them. So there are just few of them, but I will present many more later on. I just wanted to mention the structural optimization application because this was the very first one we have met, and that was the very reason why we started to try to attack nonlinear semi-definite programming. Then there is a very obvious application in control theory, in particular for bilinear matrix inequalities. I will speak about that in the second part. I mentioned that I will speak about some more examples, and I'm sure there are many more applications, and the researchers either don't know about them or they are just not aware that the problems can be solved, and they're just avoiding them. So just as a motivation, this was solved actually by linear semi-definite programming, not the whole airplane, but we were involved in the design of a rib in this part of the wing, in the leading edge. And okay, so the rib is actually hidden here, and using semi-definite programming, we have solved a material optimization problem. The result looked something like that. It was later interpreted by the engineers and built, and this is the actual design which flies in the Airbus 380. So without SDP, it would not fly, and actually it was using that approach, we saved something like 40% of the weight. But okay, I'm not saying that it couldn't be computed by other means than SDP, but it was. So just briefly, what's the background of that story? We call it free material optimization. And again, this is just a motivation why did we start at all with these things. And our aim was, so we have standard material like aluminum or steel, and we just want to, and we have given amount of that material, we have given boundary conditions, given external forces, and we just want to find the distribution of that material, or even in the further step, the properties of the material, such that the resulting structure, the mechanical structure, is as stiff as possible, or as good as possible within some measure. And the design variables here, so what we want to design here, what we want to change, are, well, either the distribution of the material or the material properties. And okay, I'll return to that. And the material properties, so we are talking about Hooke's law. The material properties, they are collected in a symmetric matrix, or actually it's a fourth order tensor, but it can be written as a symmetric positive semidefinite matrix. And what we do, if we just use standard finite element method, then let's say you can't really see the rectangles here, but imagine there are thousands of rectangles here, and we just assume that on each rectangle the material is constant, but then it may vary from rectangle to rectangle, from element to element. The material, the matrix of the material may be different, so we get a highly non-homogeneous, anisotropic material. And okay, here's the problem we get, that we want, let's say, to minimize the weight, which for some reason is measured by the trace of that E, and E is the design variable. E is that material matrix. All the material properties are hidden in that matrix. And it's a small matrix. It's a 6 by 6 or 3 by 3 matrix, depending if you're in 2 or 3-dimensional space. But there are many of these matrices for each finite element, and we want to get as many finite elements, so as fine mesh as possible. Okay, so we minimize that, and the physics tells us that the material should be, let's see, the material matrix should be positive semidefinite, which basically means that if you press on that it will not blow up, so it will comply under pressure. And there are a couple of more constraints, and you see what we get is basically semidefinite programming problem, because the variable is a matrix. The matrix should be positive semidefinite. And in fact, if we add some technological constraints, like constraints on buckling or vibration of the resulting structure, we get a nonlinear matrix inequality constraint, which has to be added to that. And this may be a large matrix. There are many small matrices, so this is a pretty difficult problem to solve. Any finite elements, so triangles, whatever.
Always planar, I mean.
No, we can of course do 3D problems as well, 3-dimensional problems, and then we would use. Rectangles are better because you get nicer picture. That's the only reason, in fact. And well, mind you, the picture is actually the result of that. So it's not really the number, but this is what the engineer wants to see. The picture tells me that, okay, here the material should be very stiff in the red region, and it should be weaker and weaker, and these are very regions with very weak material. And these pictures, they show the properties of the material. So if I want to, for instance, build the material as a reinforced composite, then these would be the directions of the fibers I want to put in some resin matrix.
It looks all like surface. Doesn't look three-dimensional.
No, these examples are two-dimensional, but I don't have 3D examples. But yeah, we computed 3D examples. It's actually tricky to plot these things in 3D, so that was the main problem of ours.
This last condition, the last condition, this APU Lagrange equation associated with the constraint above?
Sorry?
Is that an Euler-Lagrange equation?
No. That's this is basically just the buckling constraint. So this says that the critical force before the structure buckle like that is above 1. So that it does not buckle. So it's basically an eigenvalue constraint, but it's nonlinear. So this is basically a generalized eigenvalue problem, but with a matrix which depends nonlinearly on some input. Okay, so that was, say, the first part of the motivation that we really started with, first with the application, and that motivated us to develop the code. And as I've said, I'm sure there are many more problems the researchers just don't know about. As an example, let me show 3 stolen slides. So just 4 weeks ago, I heard the talk of Venkat Chandrasekaran about conic geometric programming. So he introduced that. So these are not my slides, those are his slides. He introduced that as a new class of optimization problems. And what it is, it's just a geometric programming problem, which in the convex formulation is written here. You see, we minimize some linear function subject to log C exponential of this inner product here. And okay, that if you forget this part here and if you forget this part there, that would be a geometric programming problem. But now he introduced, let's say, a new class of problem, assuming that X belongs to a cone, and for instance, it can be a cone of semidefinite matrices. So X would be a matrix, this would be the Frobenius inner product, those would all be matrices, and what you get by that is, in fact, a nonlinear semidefinite programming you have to solve if you want to solve these conic geometric programming problem. And Venkat gave many applications of this conic geometric programming. So it's just an illustration that there are problems out there which are nonlinear SDPs, and people are just not aware of the fact and of the fact that there is a way how to solve these problems, because Venkat proposed to develop a new algorithm for that, but actually it can be solved directly. So those are some. I'm not going to go through these applications anyway. I don't understand most of them. So let me return to my slides. Okay, so it's nice to define a complicated problem, but we want to solve it. So how do we solve that? The first obvious way, or the first obvious idea, would be to take the existing algorithms for linear SDP and just try to generalize them to nonlinear SDP, just like people did it in the 19th for nonlinear optimization. Also going from convex to non-convex with the interior point methods. So the interior point methods, most of the SDP codes rely on that method, at least the general purpose SDP codes. It can be generalized to nonlinear SDP using the log barrier, so just the primal or dual, however you look at that. This was actually done 10 years ago, or even more, by Florian Jere and Friedman. There is another way, again, an obvious way, take the sequential, an idea taken from nonlinear programming, where SQP method is one of the most popular alternatives to interior points. So why not to try SQP for SDP, so like sequential SDP methods. And there's a couple of theoretical papers, but in particular, this one shows that it's actually not the best idea. In fact, none of these methods work well in practice, or there is no code coming from that at all. So there are quite some papers were published, but there is no code available for that, and it turns out that some of these results, like here, are actually negative. That they show that for SDP you cannot repeat the success which you get for NLP. And there is another class of methods which was not only proposed by us, that there are other people who worked on that, and it seems that that's probably so far the best way how to solve, again, general purpose, not specialized, but general purpose nonlinear SDPs, and that's augmented Lagrangian methods. And there's a couple of papers by Abkarian and Noll, by Defenk and Yesun, and also by Michal Stingler and myself. So Michal Stingler is my co-author in all that development. And okay, so let me talk about our particular method, the augmented, let's say, generalized augmented Lagrangian method. And so let me first talk about the collection, and then I will switch to the algorithm. So in the last years, we were developing the software collection, which is called PENON. PENON stands for Penalty Method for Nonlinear Optimization. And it's, in fact, a collection of codes for nonlinear programming, linear semidefinite programming, bilinear matrix inequalities, and the combination of all those. And the key idea is to have one algorithm, one engine which solves all that. And I will speak about that algorithm in a second. So what we have available is a code for standard nonlinear programming, and those are the interfaces you can use. The code for linear semidefinite programming, then for problems with bilinear matrix inequalities, and recently, or 2 years ago, we finally developed the code where you can combine everything. So nonlinear constraints, linear constraints. Well, I will speak about the formulation a bit later on. Now, the new thing we have, and that's what I will speak about in more detail, is PenLab, so I can skip it now. And what's in progress, what is still missing, is a code for second-order conic programming, which, again, in the spirit of all that, which should be nonlinear second-order conic programming, and we should be able to combine it with NLP and SDP. So when this is ready, you should be able to have SOCP constraints, NLP constraint, standard variables, matrix variables, all that in one problem. And okay, just to show that it's not only nonlinear SDP, that the whole idea, or that the algorithm and the code is really competitive also for standard linear semidefinite programming. I just wanted to show these two examples, that the whole thing is really efficient. And okay, I have two examples. You see, that's the dimension. Okay, we have standard linear programming. N is the dimension of the, okay, that's the dual formation. So N is the size of these. Sorry. N is the number of these constraints, so the dimension of the dual variable, and M is the dimension of this matrix variable here. And you see, we have what is presented here are two versions of the code. This is the standard code, and you can say that you can replace basically this column by any interior point code available, like SDPT3 or Segume. You would get more or less the same number, because most of the time here, that's the CPU time in seconds, most of the time is spent in solving a linear equation of this size. So we have matrix of this size, and the matrix is full. So there is no way how to save that by different algorithm, how to save time by switching from augmented Lagrangian to interior point, because 95% is done by the linear solver. And okay, this is to demonstrate that if we switch from the standard linear solver, Cholesky factorization, to iterative solvers, which is done in our code, you can save lots of time, and you can also save lots of memory. No one is able to solve this problem, because you would have to store the matrix of that size, a full matrix of that size, in the computer. While here we don't need to store that matrix, and you can see we can solve this, let's say, huge problem for linear SDP in about half an hour, less than half an hour. And the same, so that's one class of extreme problems with very large n, so very many constraints and sort of large variable here. The other extreme is that that number goes up while the number of constraints is kept fixed. And also here we can go, we can solve these problems quite efficiently using the most efficient version of the code. Again, you can imagine here any other interior point code available, and well, that would be the speed up. So that's just to show that the code as such, even for linear SDP, is rather efficient. So now, what is the algorithm behind? So first, I need really to define the problem I want to solve. Okay, so we have this NLP part, but now we can have different kind of variables. The standard variable, vector in Rn, and a number of matrices of different size, perhaps. The matrices are symmetric. So we have these two, let's say, sets of variables, x and y, and all functions f, g, and h are general nonlinear non-convex functions, and they may depend on x, and they may also depend on the elements of the matrices y. And in addition, so far it would still be an NLP, even with the matrix variables, because you would simply vectorize these variables. But then, to make it an SDP, we add this constraint on the spectrum of the matrix, on the smallest and the largest eigenvalue of all these matrices. Well, this looks like quite a special problem. Where is my nonlinear matrix operator? But just using slack variable, you can convert any nonlinear SDP into that problem, and all the nonlinearities will be actually hidden in this equality constraint. I have a slide about that. So if we have a general nonlinear operator, just by introducing this slack matrix variable, it should, then we have just this simple inequality for that matrix, and this would be put in the set of equality constraints. So that's the problem we solve with Pennon. And what's the algorithm? We are using the funny colors here. Well, okay, what is the algorithm? The key idea, it's a barrier type algorithm. The key idea is to penalize the infeasibility, just like in any other penalty method. And what we do, we replace the standard, the original inequality, by a penalized inequality, or you can call it by scaled, non-linearly scaled inequality. The penalization or the scaling is done by some penalty function phi, which has a number of properties. It's convex, it's smooth, it goes to infinity somewhere, it goes to 0 somewhere else. The main order properties serve the purpose that if we replace the original inequality by the penalized inequality, we will get the same, that these two inequalities are equivalent. So it's just the scaling of the original nonlinear function, and as always we have some penalty parameter p, which says how much do we scale, so that p goes to either to 0 or to infinity in the end. And okay, we do that for the standard inequality constraint, for the standard function g, and we do the same for that matrix inequality constraint, if I look at that as a matrix inequality, using some matrix function phi, which has just the same properties, and again, the properties should guarantee that we have this inequality. This equivalence, at least on the feasible region, or perhaps on a region which is slightly bigger than the feasible region. And because of this equivalence, we can replace the original inequalities by these scaled inequalities. And so we get a new problem, a scaled problem. And for that problem, we write down the Lagrangian function. And we can view that Lagrangian function as sort of augmented Lagrangian function for the original problem. And okay, it's very long. There are many letters here, but there is nothing special. It's just that I sum up many things in here. We have the original variables, then we have the multipliers for those constraints, the multipliers for the upper and lower bound for my matrix constraints, and this is not actually a variable, it's just a parameter. That's the p, which will go to 0. And okay, here that's the part of the Lagrangian for that inequality constraint. This is for the lower bound, and that's for the upper bound on the matrices. Okay, and now the algorithm is clear, so we have this augmented Lagrangian, and we want to minimize it. So here is the full algorithm, and I have to mention that it goes back to the work of Roman Polyak from the 80s and 90s, and it was reintroduced by René Benthal and Michal Kocvara. But that was all for standard convex programming. And with Michael Stingel, we generalized that for semidefinite programming, first for linear and later to nonlinear semidefinite programming. And okay, here is the algorithm. So we take this augmented Lagrangian with these scaled functions, and in the first step we just minimize it with respect to the original variables, so the multipliers are kept fixed. And of course we don't minimize it up to very minimum, we just minimize it very approximately till the gradient is smaller than some constant. And okay, that's the main work which has to be done, because then we update the multipliers for the different inequality constraints. And the update, that's just a formula, which is based on some, let's say, heuristics, but in the end, the whole thing can be proved to work. So those are just formulas, and then, again, by some simple formulas, we update the penalty parameters. And, okay, I allow all the functions to be nonlinear and non-convex. So we can prove convergence, but as always in nonlinear programming, we can converge just to a stationary point, so there is no attempt to find a global optimum, of course. Okay, so the Pennon code takes this algorithm, so we implemented all that. Now the main question, in particular, if we wanted to implement the code for nonlinear SDP, the main question was, what should be the user interface? Because originally we thought about the nonlinear matrix inequalities, so the nonlinear functions of matrices. And in this code, so if I run this algorithm, if I return here, so here when we minimize the augmented Lagrangian, we do it by the Newton method. So we need the first derivative and we need the second derivative of that. Now if you have a matrix function, the first derivative, the gradient of that, it's a, let's say, vector of matrices. The Hessian is a matrix of matrices. If we want to preserve some sparsity in that, the interface would be just nightmare. So that was actually the reason why we considered that formulation, that all the nonlinearity is in the standard functions, for which it's much easier to compute and to deliver the first and second derivative, and the only SDP part is in these simple inequalities. So for that we have a MATLAB interface C or Fortran interface, Ample interface. Ample is a modeling language for optimization, which is actually the most comfortable way how to enter optimization problems. Basically, if you just enter it as you would write it on a paper, minimize something subject to this constraint. And the great thing about Ample is that it will give you automatically the first and second derivatives. You don't need to write them down, unlike in Maple or in MATLAB or C. So if I have a look at the MATLAB interface, so what the user have to do is to provide me the function values and the derivatives. That's like in standard nonlinear optimization. So where is the difference to nonlinear optimization? I have to say that in fact some variables are matrices. And how do I do that? So we simply vectorize these matrices. Those are symmetric matrices, so those are the matrix variables. If we vectorize them, then okay, this will be just subvector in my long vector of variables, and the only thing I have to tell the code is that okay, this part, this subvector is in fact a matrix and should be treated as a matrix, which should be positive semidefinite or negative semidefinite. Okay. Important. And the same for Ample. Ample as such, that modeling language, does not support matrix variables or matrix constraints, but we can use the same trick just by vectorization. All matrices are treated as vectors, but then we need a special input file which is read directly by the code, which tells me that okay, some parts of the vectors are actually matrices, and there are some upper and lower bounds on these matrices. Okay, so that's the Pennon code. It is there. What's new about it is that it's now being implemented into the NAG library. NAG is the numerical algorithms group. It's probably the oldest still existing library for numerical analysis. So, and it should be in there in the autumn, so in a couple of months. So next time your university will update the NAG license, it should include Pennon, and it should include linear and nonlinear semidefinite programming. And as a byproduct of that implementation, we have developed a MATLAB code, because many people asked about that, which is a free open source, and it's a fully functional version of Pennon. Pennon is, as such, is written in C. This is coded in MATLAB, and okay, it's just the same algorithm. I should probably have. It's just the same algorithm, basically the same code, but it's open source, so the user can do any changes. So we see that as a way how to test ideas, and also it should be good for teaching, because the students can change. If you don't like my line search, you can replace it by your line search. If you don't like Newton method, you can replace it by anything else. So you can do as many changes as you like. Okay, yeah, well, this is the slide I was looking for. So again, it's free, open source, fully functional version of Pennon, which is coded in MATLAB. It was not coded by me, but it was coded by Fiala, which is my former PhD student, who now works in NAG, also on the full implementation. And I think he will be here in the 4th week, and he will probably talk about the code again. The basic algorithm is identical to Pennon, to the full code. Some computational tricks or some programming tricks are not implemented yet, in particular with the handling of sparsity in SDP. And okay, it's MATLAB code. So in general, PenLab, the MATLAB version, is slower, sometimes much slower than Penon, as expected. But it's not only that code because it's in MATLAB, so it allows us, in fact, to pre-program some procedures or some modules for standard NLP. We have MATLAB input, we have ample input read by the MATLAB code. I will return to that. We can pre-program procedures for linear SDP or for bilinear SDP, because what we need what the user needs to program are just routines for the evaluation of the function, the derivative, and the second derivative. But now, for linear, bilinear SDPs, the derivatives are clear. They just depend on the data. So we can pre-program that. We also can pre-program, or we did, a module for polynomial matrix inequalities. This is a conference on polynomial optimization, so I will return to that. That's probably the first code that can solve polynomial matrix inequalities. And it's easy to add more, actually. We added more for quadratic programming, for linear programming, of course, robust quadratic programming, and others. Okay, so now I will talk about this MATLAB code, PenLab, and I will show you some examples that try to persuade you that it's easy to use it. Here's again the problem we solve by that MATLAB code, by PenLab, and it's a little bit different from the problem we solve by Penon, because we now allow this general nonlinear matrix inequality. So that's not possible in Penon. It is possible here. In Penon, we avoid it by the slack variable. Here we can handle it directly. And okay, now everything the user has to do if he wants to solve, or if she wants to solve the problem, they have to prepare a structure, which is a MATLAB structure, which is, okay, I call it PenM, but of course the name is arbitrary, and it contains the basic data about the problem. And once you have that, then you just call PenLab, which crunches this input and creates some MATLAB class, and which again I call problem here, and then you just solve that, and the results will be obtained in that class. And okay, the difficult part, of course, is again in these routines, which the user has to provide, the routines for function values, gradient values, and Hessian values of all these functions which are involved in that formulation. So let me show let's start just with a simple example. Okay, quadratic programming here, no SDP so far, just a linear objective, quadratic constraint. And this is the full input. That's all you have to do. See, you say, what is the number of variables? 2, x1, x2. If there are some bounds on the variables, yes, we have a bound, a lower bound. Number of nonlinear constraints, we have 1 nonlinear constraint, the quadratic one. Okay, yeah, that's the upper bound of on the constraint, it's 1. And then the functions, for the function value, gradient Hessian. But because the functions are so simple, you can do it in one line. And you see, so that's the objective function, the gradient. It's a linear function, so there is no Hessian. And the same for the constraint, this. So you call, define that structure PenM, you call Penon with that input, and then you just solve the problem. So I'd like to stress out that even if you forget the SDP, that in fact PenLab gives you a free MATLAB-based solver for large-scale NLP, so it can be viewed as an alternative to the optimization module in MATLAB, which many people hate. And okay, I didn't compare it directly, but okay, it is an alternative, and it's free, and you can do changes in that. But okay, our main goal is to include matrix constraints, linear and nonlinear. So here is a toy example, which goes back to Dominic Knoll, of nonlinear SDP, but you see the nonlinearity is in fact just in the objective function. So we have quadratic objective function and a linear matrix inequality. How do I code that? And switch to MATLAB. Yeah, that's the code. So let me show once again the problem. We have quadratic objective function, and we have this standard I here, which depends on those two variables. And you see, this is the full code. So let me go just here. The objective is a quadratic function, so just like before, I define the objective function just in one line. That's the gradient, that's the Hessian of the objective function. And then I have the matrix inequality. So all I have to say is that I have one linear, so this number of A, like matrix linear inequalities, that's one. The lower bound on that is 0. The matrix should be positive semidefinite. And here's the matrix inequality, and you see it's just sum of xi, ai plus b, and the ai are the data matrices which were defined on the top. And the gradient, those are just the matrices ai. So even for LMI, you can define these functions just in one line. Okay, here's another example, but it's basically just the same. So let me now switch to more practical examples to illustrate that we need nonlinear SDPs and that PenLab and Penon can solve these problems. The first example here is my favorite one, is the nearest correlation matrix with some additional constraint, which will come later. The nearest correlation matrix is this simple problem that you have a given matrix H, which was supposed to be a correlation matrix, but it's not. It's slightly perturbed. So you want to find a matrix as close to possible to that one in this L2 sense, such that X is a correlation matrix. So the diagonal numbers are ones, and it's a positive semidefinite matrix. But you want more. So if you solve this problem, often it may happen that the resulting matrix has condition number infinity, and the smallest eigenvalue of the matrix is equal to 0. And in the application, you try to avoid this situation. So the typical constraint would be that the condition number, not the smallest and the largest eigenvalue, but the condition number as such of that nearest correlation matrix must be bounded by some number, k20, for instance. Well, how to formulate that constraint? The simplest way is to say that the resulting matrix will have exactly the condition number equal to 20, and then we use that transformation of variables. We just multiply the original, we just divide the original variable by some z, so those will be some new variables, such that the condition matrix of the condition number of that matrix should be bounded by k, but using that transformation, it just means that the condition number of x, or the eigenvalues of x tilde are between 1 and the condition number of k. So just fix the interval by that transformation. And Okay, then we replace the original variable by that new variable, the same here, and okay, we have this additional constraint here. And you see now it is a truly non-linear SDP problem. Before the original problem, it had quadratic objective function, but linear matrix inequalities here, or linear SDP, and it's a convex problem, so as such it can be actually solved by specialized codes much faster than by a general purpose code. But once you add some other constraint like that, then we have a true nonlinearity here. We have a bilinear, so these are both variables, so we have z times x square, and again we have the bilinear term here. So here's an example. If we solve the problem with a 6 by 6 matrix for some original matrix, then what we get is, for instance, a matrix like that with these eigenvalues, and you see that indeed the condition number, the criterion was that the condition number should be smaller than 10, and indeed it is exactly equal to 10. Let me just show the code. This pointer. The code for that problem.
I have a question. Wouldn't you expect that the nearest correlation matrix has lower rank if it's on the boundary of this vector? So I start with a matrix outside.
With
I want to find the closest point.
yeah,
So
without that
value should be 0.
yeah, without that constraint on the condition number, yes, and that's what typically happens. But that's why we added that constraint. So I wanted to show the code, which is in here. So okay, the code to define the problem, it just says what are the names of the functions where you define the function value, gradient, and the Hessian, plus the dimensions of the problem. So there is nothing interesting here. But then, for instance, if you want to define the objective function, which is that x times z, the whole thing square, or minus the original matrix, the whole thing square, you see you can do it just in 2 lines, where this H is the data matrix, which is not correlation. This is my matrix variable. That's this additional, the scaling variable. You see, you basically write what you would write on the paper, and you minimize the square of that. The gradient, again, that's just a few lines, 4 lines, 3, and the Hessian also just a couple of lines in the MATLAB code. So it's quite easy to program these things, to be able to solve that by PanLab. And okay, yeah, I wanted to mention that here with PanLab we solved some toy problems, small problems for this nearest correlation matrix. But in fact, we also use it in the big code, in the C implementation of the code, and we have a special version which is called PanCore. And in fact, we can solve very large problems with very large matrices up to this dimension, with some additional constraints. Okay, I don't need to go into the details here. Well, yeah, I mentioned that we have the ample input for NLP, and that with PanLab you actually get a MATLAB solver for nonlinear programming, but not only for nonlinear programming, but also for nonlinear programming with ample input, which is normally not included in the MATLAB optimization toolbox. And it's pretty easy to solve these problems. We pre-programmed, because we have the automatic differentiation in ample, so we pre-programmed just the calling of the derivatives, first and second derivatives. So all you have to do, if you want to solve an ample problem, first you have to run an ample code to translate your problem. And let's say if the name of that translated, this produced ample file is, so this is one of the problems, chain 100. Then you just call the pre-programmed routine NLP define, which will define the structure pen M. You solve penlab and you call penlab and you solve the problem. And of course you can put that into just one routine. So everything, if it's in ample, you can solve it directly just by giving it the name. And because we can solve the ample, the problems defined by ample, I can also compare the behavior or the speed of the original code written in C with the MATLAB-based code, just to get an idea how much slower is it if you program everything in MATLAB. And it is much slower for matrix constraints. But there are no matrix constraints, those are just standard NLPs. And for NLPs, you will see that it's actually not that much slower because, because of various reasons. That's a set of examples which is called COPS collection, which basically mainly comes from PD constraint optimizations. So all these are basically discretized PDEs. That's the number of variables. So those are not small problems with thousands of variables, thousands of constraints, and that's a different type of constraints: equalities, inequalities, box constraints, and mixture of all that. Here is the CPU time in Pennon for Pennon, for the C code. And you see it's seconds. This is the largest number. That's the number of iterations. And for penlab, you see the CPU time is worse, but not always. Sometimes it's even better. We may have a different number of iterations because, as I've said, the numerical tricks, the programming tricks, are not the same in this code as in this code. But basically, the behavior is about the same. How come it can be even faster than how come that the MATLAB code can be faster than the C code? That's a trick, because now everything depends on your computer and on various versions of software. In this particular example, it was because most of the time is spent in dense Cholesky factorization. The MATLAB has the LAPAC Cholesky, so it's pretty efficient code. And my implementation of MATLAB used 2 cores of the computer, while here we just used 1 core of the computer. So it's really, MATLAB can be faster because it can cleverly use your computer more cleverly than some other codes. So, yeah. But in general, of course, the numbers are worse. Right. So I've said we have more pre-programmed modules for linear SDP. What is the only input? Vector and a matrix or set of matrices, plus some numbers about the dimensions. Of course, the derivatives are obvious. So if you, for instance, have your linear SDP problem in the SDP-A format, which is an ASCII format, which basically stores the sparse matrices in the sparse way. So if you have that file, that ASCII file, you just call it, and that's that's the routine which is part of the penlab distribution. Then you call that, and you solve the problem. And again, of course, you can put that just into one single command with that parameter. The same for bilinear matrix inequalities. What do I understand by bilinear matrix inequality? We have this linear part, sum of xi, ai, and we add a bilinear, or actually it's not bilinear, it's quadratic part, which just in the same spirit. So we have all multiplication of xk, xl, and they are multiplied by a matrix which may be there, which may not be there. And again, the data are just these matrices. So the character of the functions is clear. We can predefine the derivatives and the second derivatives. Now we can go one step higher. We can go to polynomial matrix inequalities. So instead of just quadratic terms, we can consider a general polynomial term in the variable x. So again, the variable is x. We may have a quadratic objective function, doesn't matter. And then we have this constraint here, so that matrix should be positive semidefinite, and that is actually a polynomial, so that this ki is a multi-index with possibly repeated entries. So here you have all the monomials, which may or may not be multiplied by some matrix qi. And again, the only input are the matrices, so it's easy to reprogram it. We have some way how to enter these matrices, so all you have to do is to define those matrices, or here I just load those matrices somewhere. Here we translate, that's the predefined module, translate those matrices in the user-friendly format into our format, and okay, solve the problem in these two commands. There are other pre-programmed modules where you just, all you have to do is to provide an input for the nearest correlation matrix, which I just mentioned, for trust topology optimization, which is a similar problem to that I mentioned at the very beginning. For static output feedback, I will talk about it in the second hour. For robust QP, again, I will talk about it in the second lecture. Okay, so that's the robust QP. Let me skip it. So, okay, that's the conclusion of the first lecture. That there are applications for nonlinear SDP. There are other applications. So I will talk in more details about the applications of where do we need polynomial matrix inequalities. I talked about that. If I have time, I will talk about sensor network localization, which again can be formulated as a nonlinear SDP. And I will try to persuade you that the nonlinear formulation is better than the linear one. I will talk about approximation by non-negative splines. I will not talk about some other applications in financial mathematics we are working with together with Prof. Werner. MPEG, so mathematical programming with equilibrium problems. What is it? It's basically a bi-level optimization problem. Okay, you want to minimize a function of two variables, and the main constraint here is that one of the variables, let's say x, solves another optimization problem. Let's say minimization, we minimize some g, where x is a variable and y is a parameter. So the data of that problem depends on the parameter y. X is the solution, and the solution is another variable in here. So as such, it's a bi-level programming problem, but the standard way how to solve these problems, or one of the two standard ways, is to write down the KKT conditions for that. In particular, if this is a convex problem, you write down the KKT conditions. So you will get a set of linear and nonlinear equalities and inequalities, and you get a standard NLP by that. Perhaps with some ugly equalities, but let's not talk about it at the moment. Now, if you replace that standard optimization problem by an SDP, linear SDP, you write down the optimality condition, you will get a set of matrix equalities and inequalities. The complementarity will give you the nonlinear equality. So in that way, we will get a nonlinear SDP from this unpack, and the way how to solve that we work with, on that we work with Daniel Half, who was supposed to be here, but he's not. Other applications, I mentioned the structural optimization, that's the very first application I mentioned at the beginning, and there are a couple of more, and of course any hint is welcome. If you know about nonlinear SDP, please let me know. And finally, so there is a free academic version of the full code, Pennon, but more importantly, you can download the PenLab code, the MATLAB version, from the NAG website. I'm not sure if it's set up yet. It will be set up by the 4th week when Jan Fiala will talk about that. But if you are interested, you can just send me an email and I will send you the code. So that's the end of the first hour.
There's still time for 1 or 2 questions.
The nonlinear semi-definite programming, how do you deal with infeasibility issue? Would your code give a certain kind of certificate, say indicating your problem is empty?
No. So, okay, the only thing we can do, and we do, is some initial scaling of the problem. But of course, it may happen that the problem is ill-conditioned and the code just doesn't work. But that's all I can stand up and
Other questions?
I'm sorry, doesn't work, it means that it converges and converges, or runs and runs, but it doesn't stop.
So when you have several solutions, the optimization problem, this iterative.
You will find one. It depends on the initial guess.
So is it in the interior?
It is. Well, it can. It does not have to be. It can be slightly away. So it's not an interior point method. It's an augmented Lagrangian. So we can approach the minimum from outside the feasible region. So in the end, let's say, if the matrix should be positive semi-definite, the smallest eigenvalue can be slightly negative, 10 to minus, well, up to your precision.
Okay, so let's thank. Oh, one more.
Sorry.
Last one.
So you had one example with a disk in R2 as feasible region, I guess, right? And you started with an initial point outside, that is like 2, 1 or something. So it doesn't matter if you start with an infeasible or feasible point?
It's not an interior point method. We allow infeasible points, also infeasible starting points.
So, thank you, Michael. And we continue at 11.